Hello everybody. In this lab, our objectives include 1. Understanding the principles of gas transfer. 2. Determining the effect of water quality on the saturation concentration of dissolved oxygen, beta. And 3. Determining the effect of water quality on the overall oxygen transfer coefficient, alpha. The concentration of the reactant in the aqueous phase relies on the rate of mass transfer from the gas phase to the aqueous phase and on the rate of the aqueous reaction. For example, in the case of activated sludge treatment of wastewater, the addition of oxygen to the aeration tank provides dissolved oxygen used by aerobic bacteria to biooxidize soluble organic compounds to derive energy and produce biomass. This process requires substantial input of oxygen from the gas phase, usually air, to the aqueous phase. Several theories have been proposed to model the transport of material from the gas phase to the aqueous phase and vice versa, including the two-film theory. In wastewater situations, when aeration is the goal, the gas transfer is usually reaction rate limited. The mathematical model that describes the process of gas transfer in the two-film theory is as follows. In wastewater, alpha and beta are significantly affected by the water quality, and in particular the dissolved solid concentration. Unfortunately, alpha and beta cannot be calculated from first principles and must be derived experimentally. This lab will focus on oxygen transfer in municipal wastewater treatment applications. Methods for estimating gas transfer rates can generally be divided into 3 categories: tap water, primary effluent wastewater, and secondary effluent wastewater. The primary and secondary effluent used in this lab are artificially prepared. Please wear all required PPE at all times in the lab. Lab coat, gloves, safety goggles, and with long hair tied back. Each group will examine the gas transfer characteristics at 3 different mixing speeds: 480 RPM, 960 RPM, and 1440 RPM. In one of the 3 water samples: tap water, primary effluent, and secondary effluent. Each group will perform a single run with each speed. Results from all groups will be pooled as class data. Dissolved oxygen concentrations will be monitored at 3 levels within the test chamber, the top, middle, and bottom, to create a vertical profile. The DO meters have been calibrated with respect to ambient temperature and pressure. Prior to each test run, reduce the dissolved oxygen level to less than 0.5 mg per liter by mixing the sample while sparging with nitrogen gas. Set the turbine to the desired speed using the motor speed controller, MV equals RPM. Maintain consistent aeration for all tests. Set airflow rate to 50 units, 98 milliliters per minute. Record DO at timed intervals, i.e. each minute, throughout the run. Record the water temperature at the beginning and at the termination of each run. Using the general relationship for gas transfer, determine the KLA value for each sample. The equation can be derived by integrating equation 1 to give the following. Evaluate the KLA 20 for each sample and mixing intensity, then evaluate alpha and beta for samples 2 and 3 for each mixing intensity. While operating the turbine mixers, make sure that items do not become wrapped around the turbine shaft. Do not put your hand into the reactor while in operation. After this lab, you should know how to use a lab-scale reactor to estimate the KLA, alpha, and beta of a larger gas transfer reactor. This data is important for the scale-up process.